For a decade, radio telescopes detected mysterious signals from deep space. Bursts of energy appeared with clockwork precision. Every 2 hours, without fail, a pulse arrived. Each one lasted less than a minute and a half, then vanished. No one knew what sent them. The signals came from nowhere on any star catalog. They didn't match the patterns of pulsars, those lighthouse-like neutron stars that spin at the edges of death. They didn't fit any model in the textbook. The mystery began in 2015. The Low-Frequency Array, a network of radio antennas spread across Europe, recorded one of these signals in archival data. The signal came through, clear and distinct, then stopped. The question hung in the silence. What was out there, 1,600 light-years away, firing pulses at us with such mechanical regularity? Radio astronomers called them long-period radio transients. Transients because they came and went. Long period because hours stretched between each burst. They were rare, unpredictable in origin, and they challenged what astronomers thought they knew about how distant objects produced radio signals. Conventional wisdom said that long-period radio sources came from isolated objects, neutron stars in their final decay, or perhaps something stranger still. The assumption was that only a solitary object, spinning alone in the dark, could generate such a pattern. For years, the signals accumulated in archives. Telescopes recorded them. Astronomers plotted their arrival times. They measured the frequencies. They looked for structure in the chaos. But the pattern resisted explanation. 20 years of observation built up, and the answer was sitting there in data that already existed. It just needed someone to ask the right question. That person was Iris de Ruiter. In March 2025, when her work appeared in Nature Astronomy, she was a postdoctoral scholar at the University of Sydney. She had conducted the research as a PhD student at the University of Amsterdam. De Ruiter decided to examine the LOFAR archive in a different way. Instead of looking for what was unusual about the bursts, she looked for what was regular. She noticed something others had missed. The signals didn't scatter randomly through time. They came on a schedule so rigid, so mechanical, that it seemed almost deliberately timed. 2 hours. Then again. Then again. The interval never deviated. A clock running somewhere in the cosmos was controlling these transmissions. De Ruiter pulled the signal apart, looking for hidden details underneath the noise. She analyzed the frequencies. She traced the arrival times. She mapped how the radio energy distributed across the spectrum. Then she did something decisive. She combined what the radio telescope saw with spectroscopic data, measurements of light in different wavelengths that could reveal the composition and motion of distant objects. The MMT Observatory in Arizona had looked at the same region of sky, so had the McDonald Observatory in Texas. When de Ruiter matched the radio bursts to the light signatures those observatories recorded, the identity of the source emerged. The signal came from a binary star system designated ILTJ 1001. What she found there was a dance between death and predation. 2 stars orbited each other in intimate proximity. One was a white dwarf, the remnant core of a dead star, compressed so densely that a teaspoon of its material would weigh as much as an elephant. The other was a red dwarf, still alive, still burning hydrogen in its core. But the white dwarf wasn't simply orbiting at a distance, it was actively stealing material from its companion. Gravity was pulling the outer layers of the red dwarf away, shredding them, drawing them toward the white dwarf's surface. Astronomers have a name for this, a vampire star. One sun feeding on the life of another. The orbital mechanics were precise. The 2 stars completed one full orbit every 125.5 minutes. Every time they reached their closest approach, something violent happened. The magnetic fields of the 2 stars didn't simply pass by each other, they collided. The material flowing from the red dwarf, already accelerated by gravity, slammed into the white dwarf's magnetosphere, the region where its magnetic field held dominion. That collision generated an enormous release of radio energy. The burst lasted between 30 and 90 seconds. Then the stars continued their orbit. 2 more hours passed. The pattern repeated. Charles Kilpatrick, a research assistant professor at Northwestern University's Center for Interdisciplinary Exploration and Research in Astrophysics, worked with de Ruiter to confirm and analyze these findings. What their combined work showed went beyond a single discovery. This wasn't just one odd system. ILTJ 1101 represented an entire class of astronomical objects that scientists had overlooked for years. Long-period radio transients weren't the isolated remnants astronomers had assumed. Some of them were close binary star systems, engaged in a cosmic dance of predation and magnetic collision. The implications spread outward. Every time an astronomer looked back at archival data, they would search for new systems like ILTJ 101. Elsewhere in the galaxy, other vampire stars were probably following the same pattern, emitting radio pulses, marking time with their orbital encounters. ILTJ 101 was simply the first one astronomers could finally explain. The mystery didn't resolve. It transformed. ILTJ 1101 is still firing its bursts. Its two stars still complete their 125.5-minute orbit. The magnetic fields still collide. The pulses still repeat every 2 hours, as precise as they were in 2015. And somewhere in the data archives of radio telescopes that have been running for decades, there are probably more systems waiting to be found, patterns that look like random noise until someone recognizes them for what they really are.